Okay, in this video segment, I would like to show you how to use the concept of a remote force uh, in 3D Experience Release 2022X. This will be done in the context of both a problem that is modeled with shell elements and also one with solid elements. I will do the solid elements first, and then once I'm done with that, we come and do the shell elements together. So there is this icon. There is this icon in 3D Experiences FEA Solver, which looks like that. It shows you some kind of an arrow, but there is, you know, this displaying it as if it was not applied at a point, but at the distance location. And the example that I'm going to do for you is going to be a geometry like that, a very simple clamped, basically a clamped beam. And the reason I choose a simple geometry is because I don't want to get bogged down with making complicated, parts. Now, in this particular problem, we know that the first 100 millimeter on the left side is much softer than the last 50 millimeter on the right side. In other words, I'm assuming that this right side 50 millimeter is very rigid. That being the case, and you apply a tip load at the end of this rigid, very rigid portion of the part. Now, because this is rigid, it doesn't it doesn't obviously deform, and it just moves as a rigid body. That being the case, there is really nothing to recover in this portion. There are no stresses to look at, etc., because it moves as a rigid body. That being the case, we're not going to even model the last 50 millimeters of this part. We just only do the 100 millimeter to the left. The geometry is shown here. Standard steel properties, and the load is 1000 Newton. And the remote force icon that we are discussing is actually shown here under the force. When you try to apply a force, there are these different things that you can do, and one of them is remote force. Now, uh, I have done a I've separated this rigid portion of the very rigid portion of the cantilever beam, drawn it like that, and drawn the free body diagram. And this will show you that if we are modeling only the left side, only the left 100 millimeter, then what happens is that you not only are applying a force here, but you also apply a moment. Basically, it's the force multiplied by that distance d. So this that couple is going to be applied on the right side. And I've gone to basic strength of material books and shown you that if you have a force and a moment applied at a beam, at the cantilever beam that's length L, then the total deflection is coming from the sum of these two deflections right here. And rotation is going to be the sum of these two rotations, one for the applied force, the other one for the applied moment. This is just so that we can compare our results in 3D Experience with something, and have we can have the confidence that actually we're doing it right. Now, a couple of things. We're going to, as I said, we're going to do it both with shell element and beam elements. We'll only model the 100 millimeter to the left. Oops, this is a mistake. It should be down here. It's a remote force actually, not imported force. Wrong. Okay, and here is a MathCAD worksheet calculation. So what we should be getting, the maximum deflection for the part that we model is going to be 3.5 millimeter, and the maximum stress at the wall, obviously, is going to be 9, that's 0.9 gigapascal, or yeah, or 900 megapascal. Right. Okay. So we're going to be comparing our result with this number and that number. Now, I just want to point out that if you look at the remote force dialog box, you can either specify the remote location, remote point, and then it's going to place it at that location. If you don't, then it's going to place it at the centroid of this end. So in other words, when I select this face, when I select this face And if I don't specify the remote point location, it's going to place it right at the centroid of that face. Okay, I'm not going to do this case on the left. We're interested in the case on the right. Now there is a help. There is help in 3D Experience online documentation, and I leave it to you to read it. Basically, it's explaining some of the concepts that we're going to be. So we're going to be doing the top one first, and then once we're done, we come back and do the bottom one, Michelle. Okay. All right, let's go ahead here. I already have gone to my account and create a part, using the part design icon, this part design, don't want that. So on a convenient plane, on that vertical plane, I will sketch. We'll sketch a 10 millimeter by 10 millimeter rectangle. The units have been set to SI, so this says, so 10 mm. Okay, and dimension here is also 10 mm. There we are. All right. Just want to make sure this is centered, and it is not. I didn't mean it. So this control that I wanted to draw it at the center here, but I neglected to do that. So let's make it 0. Very good. Exit. Okay, and then we're going to pad it. Pad it by 100 millimeters, 100 mm. Okay, so this is our part. We're not modeling the entire cantilever beam. The 50 millimeter on the right side, we're not gonna model. Now we also need a remote point where I'm going to actually place my force, remote force. So let's go to a point here, and coordinates x, everything is 0 except for y, which is going to be 150 millimeters. So this point is located 100 millimeter away from that left side, which means 50 millimeters here. Okay, let's apply a material. So tools, actually let me go ahead and do create. How about that? Let's go to create material. I'm going to call this thing so remote force. Remote force. Say okay. Right there, right click, apply. Let's close this window and apply to that part. Check mark. So now we're going to put in our numbers there. So double click on the material simulation. Okay, so structural, not there. Abacus multiphysics, mechanical, elasticity, elastic. And that is about 200 gigapascal plus 1 ratio 0.3. That's all we need, nothing else. All right, so very good. Now we're going to go to structural model creation. We use the standard, and I'm using a sweep mesh. This is very appropriate for a swept mesh area, mesh volume. So this is parabolic, right there, parabolic. And I'm going to select the part, and I put down 5 millimeter here as the size, 5 millimeter, and then we say update, and we're going to get our mesh the way I showed it to you on the slide, on the PowerPoint page. Okay, that's good. So automatically material and properties are assigned right there, automatically assigned. And we are pretty much, this is pretty much it. So now we're going to go to Structural model structural scenario creation. Okay, we already created a mesh here, so finite element model, and we say okay. All right, so we go to procedures. It's a static problem, static step, and I want to do exclude the geometric nonlinearity, although that doesn't hurt me or help or doesn't. I can leave it like that, but since I want to compare my result with the linear problem, superposition problem, I just excluded that include geometry. This has no bearing on the tutorial. Okay, say okay. Very good. And we're going to go to restraints, clamp the right side, or left side actually. There's the left face. I'm going to entirely clamp it. And then we're going to go to loads, and notice that on the force, we have remote force right there. See that? Remote force. You click on it. And the support, we're going to apply it on this face. This is the support. See that? The face is selected. Now, if you say reference point specified, and that's what I'm going to do, select the support, and it says now you can go pick the point. So I go and pick the point, which was somewhere here, right there. You can see that, right there. If you're having a hard time doing this thing, you can do it from the tree, right there. The point has been set. Notice that it placed the force at that location. Now, minus 1000 Newton, it flips it down right there. So it will take that moment of this about that support, that face into account later on. That's pretty much it. There's nothing else to do. So we go to simulate. I know that the model is going to work, scenario is going to work. But let's try it. Okay. It'll work. It's a simple problem. Once this is done, then we're going to do the same problem with shell elements. All right, let's do the simulation check. By the way, these things are fairly well established if you are an Abacus user. Okay, the icon may look different, the name may be different, but there's nothing advanced here. It's just that even if you're an Abacus user, advanced Abacus users, and you have not used this interface, because this is the modified version of the Abacus program buried here in 3D Experience as the native FEA solver, you will have to do some detective work to find out where things are. So the purpose of these videos uh, is to show these things for somebody who has never used Abacus before and trying to do FEA calculation in 3D Experience. Okay, that's done, and now we're going to run it. No big deal, it's going to work. And you're going to check our calculations against that MathCAD worksheet that I gave you. You better get the same answers, and we will. You'll see. So as this is running, the maximum tip deflection should be tip deflection is going to be 3.5 millimeter, and the stress at the wall is going to be roughly 900 megapascal, or 10 to the 8 Pascal. We'll see. And it's going to be done. Excuse me. The following video is going to be the same type of problem, except that I'm going to do the remote torque. Okay, so there we are. Let's close this thing. This is the step frame 0. This is the 1 meter stress. See that? It's right there, 9 e to the 8 at the wall. If you look at the displacement, it's going to be 3.5 millimeter. This is meter, 3.5 millimeter at the tip. So it worked. Okay. So now I'm going to do another problem. Same problem, except that with shell elements. Okay, so I can close these things, no problem. Or I can go and say, okay, so let's go ahead and start a generative shape design file. Okay, right there. And now I'm going to create that. Let's see now, where are we? We will create this surface. Okay, so on a convenient plane, on that horizontal plane, I will sketch and I will draw my rectangle right there. Let's dimension this thing. So this is 100 millimeters, and the width here is 10 millimeter. All right, we exit and fill this thing. So go to surface. There's a fill option. It puts a surface on that right there. Now I'm going to create a remote point here. So I go to essential. There's a point, and the y coordinate being 150 millimeters. Okay, so right there, we are. Okay. This is pretty much it. So let's apply material. We already created that material, so let's go to tool. Let me check something here. Let me check my browser, see it's already there. Okay, it's the same material, right? So right here, remote force, right click, apply. We'll close that. I'm gonna apply it to this. So the information is there now. That's pretty much it. So now we're going to go to structure model creation. Now I'm not going to use this because when you do this thing, it meshes it with 3D elements, but there is no 3D part here. So I'm going to say empty FEM because I have to do the mesh myself. Okay, good. And now we're going to go to mesh. I will use a surface quad mesh on that surface. Again, 5 millimeter parabolic. 5 millimeter parabolic, mesh it. There we are. Say okay. All right. Now, incidentally, if you don't want to see the part, you can always use the visualization management and hide things and show things. I'll just leave it the way it is. Okay, that takes care of this. So properties, now we're going to do properties. It's a shell section. And we can select this entire part. I suspect if I select it from here, it's going to take the whole part. We'll find out. Well, this took the mesh. It really doesn't matter. Cancel that. If you want to select the part, then maybe it would have worked. It's just that, let me hide my mesh. There. Okay, now apply shell section. Now I can do the part. See, it took the fill, 10 millimeter. It really doesn't matter. You could have used that meshed part. 10 millimeter, and these are good. I don't need these things. We say, did I close it? Say okay. Good. So it's meshed. Now we're going to go to structural scenario creation. The element that I selected, or the mesh, the finite element mesh mod, finite element model that I created. Okay. So we're going to make a static step procedure. Static step. Again, let's make it entirely linear. No, do not include geometric nonlinearity. This has absolutely no bearing. You can leave it the way it is if you wanted to. And now we're going to do restraints. Now I want to restrain that entire edge. The problem is that, let's see now, clamp. See, it'll give me a hard time selecting that. So what I can do is I can do mesh visualization, and for example, select the either hide the fill or cancel. One issue is that this is the I have to hide the sketch. That's another way of doing it. So let's go ahead and apply the clamp there. Okay, on that end edge is clamped, and then we're going to do apply remote force. Excuse me. That's the whole purpose of this video sector segment. So remote force. Uh, well, uh, well, first of all, the place that I'm going to apply this that edge. I want to uh, apply a force at this remote location, but the support is really that. But I want to specify the support where it's going to be applied. That point is going to be right there. Okay, and the value is minus 1000 Newton. Okay, good. So you can see that. If I had if I had not selected this point, it would have put it right there, downward 1000 Newton. Okay, that's pretty much it. Now I'm not going to even bother checking these things. I know it's going to work, so let's go ahead and run it. I should be getting exactly same, well, pretty close at least to the stress, which was 900 megapascal, or 9 10 to the 8 Pascal, and deflection of 3.5 millimeter. It'll give it to us. The difference between this tutorial and the one for remote torque is that remote torque will not give you the option of selecting a point, because a torque or a moment does not have a root. Okay, so you can, won't even let you say, here's where I'm applying the moment at this, at that point. That's something from elementary statics when we discuss moments and torques and things like that. Good. So let's kill this. There is your roughly. There is your. There is your 9 10 to the 8 Pascal. Okay. At this end, obviously this is done with shell elements, not solid element. And for the displacement, if you select displacement, you get your 3.5 millimeter right there. All right. Good luck.